Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 623. Add one row to a tree. In this video, we're going to share a solution based on breadth-first search. So here we are going to present an iterative format. So actually we have practiced quite a large number of traversal solutions in the tree context. So let's first look at the statement of this problem. So in fact, this problem is rather straightforward. So we just need to do the coding according to the adding rules given in the main statement. So let's anyway first look at the statement to digest the requirements and the problem size. So given the root of a binary tree and two values, value and depth, add a row of nodes with value to be the value at the given depth. So here the convention is that the root node is at depth 1. So here is the adding rule. So given the integer depth for each non-null tree node current at depth minus 1, create two tree nodes with value being the value given at the current left subtree root and right subtree root. And the second item is that the original left subtree should be the left subtree of the new left subtree root. Similarly for the right subtree. If the depth equals to 1, so then we're going to create a tree node with value being the value given at the new root. And then the original tree is the new root's left subtree. So here are several examples. So in example 1, so we want to add one row at depth 2. So here is the result. So this is the left subtree, is being the left subtree of the added 1. And this is the right subtree originally, and it's the right subtree of the added 1. So we can interpret example 2 similarly. So let's look at the constraint to digest the problem size. First, the number of nodes in the tree is in the range 1 to 10 to the power 4. So in particular, so this tree is not a null tree, and at most it contains 10 to the power 4 nodes. The depth of the tree is in the range 1 to 10 to the power 4, right? So the node value is in this range, and the value is in this range, and the depth is greater than or equal to 1 and less than or equal to the depth of the tree plus 1. So with that said, I guess we can directly go to the coding. So this actually is rather verbose. So here let's do this faithfully following the adding rule. So first we are going to treat a special case. Treat the case that is depth equals 1. So in this case, if depth equals 1, according to the problem statement, we're going to create a new root. So the new root will have is a tree node. The value is the value given, and the original tree will be the left subtree of the new root. So we're going to write left to be the root, and in this case we're going to return the new root. So this finishes the treatment for the special case. So next we are going to treat the generic case. So in this case, so we are going to use breadth first search, because we want to go it layer by layer. So for this we are going to use a queue. So actually we can use deck, or this is a container, so implemented in Python, or we can just use a list. So let's use a list directly. So root and 1. So here what we are storing in the queue is node and its level. So notice that here is an important assumption. So the number of nodes in the tree is in the range 1 to 10 to the power 4. Notice the lower bound. In other words, this root is not null, so we can initialize this queue like this. And then we are going to do the breadth first search. In the process, if we meet nodes with level being depth minus 1, then we are going to create new children, and then do the repointing, right? So while q, so let's get the node and the level is q pop left, right? So we're going to use the left as the head of the queue and the end of the list as the tail of the queue. So then what we're going to do is to check if level equals depth minus 1. If this is the case, so we're going to add 2 nodes to this node, and then we connect the original left subtree and the right subtree to the added new nodes. So first I'm going to get the save the original left subtree and right subtree for later use. So it's node left, and original right is node right if we have, right? And then we are going to create a new left. The new left will be tree node. The value will be a value, right? The left will be the original left, right, of the tree. So similarly, we compute the new right, right? So the new right will be tree node. Value will be the value given, and the right will be the original right. Then after this, we need to do the repointing. So what we are going to do is node left. We can do this reset because we have already saved this original left and right. So node left to be new left, and node right to be the new right. Right. So then this finished the adding nodes. So then we're going to check for the queue, for the traversal, in other words. So if node left, so what we're going to do is to queue append node left. So this way we consider the next layer of the current node. So its level should be level plus 1. So similarly, if we have node right, in other words, the node right is not null, so we're going to append node right and level plus 1, right? So this way, actually, we finish the traversal. So then we're going to return the root, because in this case we didn't change the original root. So with that said, let's first do a special case check. So here, list object has no pop left. Okay, so let's pop 0. So the deck will have a pop left. So let's do the check again. So it passes the first example, I guess. So now let's look at the generic case. Yeah, it passes all the cases. So with that said, I guess this forms a solution to this original problem. But here I want to mention one thing, because here we are using breadth first search, and then we do this check. And so we first check for level 1, level 2, then up to depth 1. Then if we have the node, then we can actually add an early stopping. So optional early stopping. So in this case, so if we check the level is larger than depth minus 1. So in other words, if it first equals depth, then what we're going to do is to return the root. So this is actually an early stopping condition. So you can break and do the return the root, or you can just directly return the root here. So let's check this, right? Yeah, it passes the condition. So also if this one, we can also use a break. So we can then test again. But I guess use a return root maybe better. So this way we do not need to do a full traversal of the tree. But if we do not include this if check or early stopping condition, so actually we did a full traversal. So after we traversed level depth minus 1, then all the others just redundant traversal. So with that said, I guess that's about it for this specific problem and this video. If you are interested in learning more about breadth first search, depth first search, and other traversals for tree or for graph in general. So you can check out other videos in my channel. So with that said, that's it. Thank you.